All right, hello everyone and welcome. Thank you for coming. So we'll see what this supposed blizzard is going to be like. It's supposed to be coming tonight. It's now officially a blizzard warning for tomorrow. Lots of snow, supposedly. We'll see. I'll see it when it comes, rather than. All right, here's a few announcements. As you know, for labs this week, there is no pre-lab. You're doing a probability and random variable review. Bring your calculator. Bring your formula card. Start bringing that regularly to classes. And your clicker for some review questions there. Homework 2 will be submitted for you tomorrow night at 11. Couple reminders. When you're making a graph from SPSS, what should be included with that graph? A title and your name. And if you are drawing your uniform distribution for number 8, there's lots of ways you can do it. I go into Word and I pull out the shape and make a rectangle and put in a couple text boxes just to put labels and values on the axes. I make it that way for a solution set. You can draw it by hand. You can scan it in, take a picture with your phone or camera so you can make it a JPEG. As long as it's readable so we can see what you've written, that works well too. I have students who will do it in a PowerPoint or Word and print screen to save it as a JPEG and upload that. Good. Questions or comments on homework 2? You've all started, I assume? I've looked through most of those questions, I hope. On the next slide, here's your exam 1 info. It's also up on C Tools. There's where you go to take your exam on February 17th. Based on the lab section you are attending, we have the rooms starting at 5:30. We set them up, let you in when they're ready. We have the rooms past 7:30. If the room actually starts the exam at 6:03 or 6:05, you'll have a full hour and a half to take the exam. We write the exam to take about an hour. You're free to leave when you're done. There's always a distribution, some leaving in 45 minutes, some taking the full time, but most are somewhere in the middle. So we do have the rooms past 7:30. If needed, we'll give you that full hour and a half from when we start. The basic page number for your lecture notes, page 93 is really the last material or content, and we will be covering that, if not the end of Thursday, perhaps a little bit on Tuesday next week. But then that's the end of the material for exam 1. And the Sunday the 13th is the day we have MLB Odd 3 to do the review. I'll be putting up some review questions, definitely by next week, that will be covered at that review. It'll also be captured and posted on C Tools, iTunes U, if you are not able to attend the actual review itself. All right. Also in the rooms, we will have you put your backpacks and bags along the wall because it's just too hard to climb in and out and don't want that material right there. So the less you bring, the better. You need to bring your ID card, things to write with, and a calculator with good working batteries. Everything else will be provided, the formula card and the exam. All right, questions or comments before we recap where we are in our material? Any question or comment at all? I'll put this slide up over the next few lectures. It's also up on C Tools for you. You can turn to page 67 for a recap here on these 2 normal approximation results. Page 67. Both of these results appear on this page. They are both normal approximations to a statistic. The first one is the one from actually chapter 8 that you do have to use on your homework too for one of the questions. The first one talks about how you could take a binomial variable that actually has a binomial distribution, and approximate it as being normally distributed instead. It says if you have a binomial variable, which is when you're counting the number of failures or number of successes, and your sample size, though n, is large. And how large? Well, you need to have at least 10 successes and at least 10 failures expected in your sample. So very minimum, at least 20 observations. One of your homework questions has only 9 patients initially, right? 9 patients are given this treatment and a certain percent are expected to fail. You work through some probabilities. 9 is not large enough to do any kind of normal approximation. But then the follow-up question goes to 90 patients. And 90 patients, when you work out your NP and n times 190, that works to be able to use the normal approximation to calculate the probability it asks you to do under a normal curve. The mean and standard deviation for this normal approximation are those for the count. N times p is how many you'd expect in your sample to be successes, whatever you're counting, the count. And that square root with the np1 minus p is, again, the standard deviation for the count variable. When you're counting how many said yes. And then we had a follow-up normal approximation that we use for the distribution for not the count, but p hat. If you take your count and divide by the sample size, you've got the proportion who said yes in your sample, called p hat. So just going from the count to the proportion allows us to have this corresponding approximate model that works for the sample proportion. Looks somewhat similar. There's still n's and p's everywhere, but now we're centered around the true p instead of the n times p for the mean. So I have students saying, which of these do I use? Again, it depends on what kind of probability you're being asked about. Are you asking the probability of seeing at most 10 failures in your sample? The count is what the probability is about? Or is the probability or model talking about for a proportion, p hat? So we use this model at the end of our last class to come up with what we'd expect to see for the proportion who said they voted in the recent election. That was the model for the sample proportion. This shows you how the sample proportion would vary from one sample to the next. So both of these results are on your yellow card. And one of them talks about for the binomial, that's for the count variable, and the other is the corresponding model for the proportion. They are related, obviously, because you just divide by that n. They have the same requirements of the at least 10 rule before you can use these normal models. And the normal models allow you to have a frame of reference of what you'd expect to see. And we'll be talking about this standard deviation here in just a few moments. So on that homework question, it says to find the probability, and it says to state the conditions and verify those conditions so that you can use the normal approximation. It tells you to use the normal there, and you do have to then show me that n times p and n times 1 minus p are at least 10 for both, and you had 90 as your sample size. So let's take a look at this standard deviation a little bit more. Why do I like this standard deviation better than the one for the count? Standard deviation has here the n on the bottom, the sample size in the denominator. So what happens when the sample size gets larger and larger to that standard deviation? It gets smaller. And if my standard deviation is getting smaller, then my sample proportions that I could be getting in my survey would end up being closer to the truth, closer to the true value of p. I like that kind of standard deviation better than the top one. The top one is for counts. And if you're taking a larger sample size, well, then there's even more possibilities for what the count could be. So the standard deviation actually gets bigger rather than smaller. Top of the next page. More on that standard deviation. Actually, page 69. Do you remember how we like to interpret a standard deviation? as roughly an average distance of the values from their mean? Well, this is now a standard deviation, not just for a set of data and not for a population like sigma, but it's the standard deviation for p hat, which is a quantity that varies. And it varies from sample to sample. So here's the interpretation for such a standard deviation. It's approximately, so I'm starting out with the roughly or approximately part. It's approximately the average distance of the values from their mean. Of the values. The values are now p hat. It's showing me the average distance that the values you could have for p hat would tend to be from their mean. And where was that model saying the mean was? The true proportion p. So this quantity would tell me how far away I'd expect my sample proportion to be from the truth on average. It's a nice quantity, a nice measure of accuracy of your estimate p hat. Now, the only issue I have is I usually cannot calculate that quantity. We did it last week, Thursday, because we said we knew that 39% had actually voted in the election. So we had the true value of p in that particular problem. Many problems that we come up with, we're taking a sample from a population, we're trying to learn what that value of p is, use our sample to learn about it, we don't have that true value of p. So I can't compute that standard deviation, even if I wanted to. So what do? I don't know the value of p, but I just took a sample, and my sample gave me p hat. And there's an estimate of p right there. So let me put in the hats over these p's, and you've got this new term that's called a standard error. A standard error is an estimate of the corresponding standard deviation. I put in the p hats, that's a number I can calculate, even with just my one sample that I took to estimate that true proportion p. So the only thing that changes in the interpretation is the word estimate there. And it's kind of redundant, you know, we're estimating approximately, but that is an estimate of the standard deviation. So it estimates that rough average distance. I'll be able to compute that to have an idea of what the yardstick is, and then I can use that yardstick to go out a few each way from my best guess to make that confidence interval that I want to use and report. We'll use this to create a range of values. We'll start at our best guess. We'll go out a few standard errors, since I can't go out standard deviations. And this will be the basis of what we call a confidence interval. Now, haven't you already seen a confidence interval for a proportion before? Right? You've got p hat, and then we call this thing a margin of error, that you went out plus and minus. What was that margin of error formula? 1 over square root of n. That's what this expression will turn out to be when we want to be a little conservative in our estimate, 1 over square root of n. But it comes from taking and going out a few standard errors. That's where the 1 over square comes from. What if I want to be 95% confident? How many standard errors should I go out? About 2. If I want to be 99.7% confident, I'd go out 3. So those are some of the ideas. Let's try them out. Let's look at the love at first sight. Watch, watch, watch. Oh. We have a random sample of 500 adults, and 300 say they believe it, love at first sight. How would you answer part A? I just want an estimate right now of the population proportion who believe it, love at first sight. Now, I had some students on an exam say we can't give you that answer because we don't know the population proportion. I didn't ask you for the population proportion. I asked you for an estimate of it. I'm asking for an estimate of p, which means give me p hat, the rate in your sample that said yes. So I'm asking for an estimate of the population proportion, p hat, which would be what? Pretty easy here. 300 out of 500, or 0.6. And if you write things with percent, it's fine. Just make sure the percent sign's there, rather than just saying it's 60. So our estimate right now is 60%. If I had to give you an answer for what you think the true proportion of adults who believe at love at first sight would be, I'd say 60%. although that's probably not exactly true. It's probably not the true proportion. Sample proportions like this one are going to vary. If I were to take another sample of 500, will I get exactly 300 saying yes that time? Probably not. It's going to vary. The standard error gives me an idea of how such a sample proportion will vary from one sample to the next. Let's take a look at that. Let's calculate the corresponding standard error of our estimate. That means I want the standard error of our estimate p hat. That's not the standard error times p hat, that's the standard error of p hat. Sometimes when that's in a formula, I get students putting in the standard error and then they multiply by p hat again. It's the standard error of p hat. And our formula for that is taking our best guess, 1 minus that p hat over the sample size. So we had 60% as our estimate. Nice large sample size of 500. Now we're talking about the standard error of p hat. P hat is already restricted to be between 0 and 1. It's a proportion. So standard errors are even much smaller than that in that range. So do watch calculating these things and make sure you're able to get them. Let's just give you a final answer. That's 0.22, about 2.2%. So sample proportions, p hat values, will tend to vary from one sample to the next. They vary from the true proportion by about 0.022. I'd estimate how far away would they be from the truth? On average, about 2.2% away. So can we use that to come up with a better estimate than just saying 60%? Let's go out a little bit each way, using our yardstick here, to give a range of values that would be reasonable for the true proportion. It says use that standard error to provide an interval estimate rather than just a point estimate, rather than just say 60% is the answer. Give an interval estimate with 95% confidence. So if I wanted to be 95% confidence, how many standard errors should I go out? About 2. So we'll go out 2 standard errors from our 60%. 2 of the 0.022s would mean my margin of error is about 4.4%. Now if you did 1 over square root of n, it would be reasonably close to that. But the 1 over square root of n we'll see by the end of class today where it ties in with this expression. What do we get for a range? From 0.556 to 0.644. 55.6% to 64.4%. So rather than saying I'd estimate the rate to be 60%, I could say I'm 95% confident that the population proportion of all adults who believe and love at first sight is somewhere between 55.6% to 64.4%. I'll give you a range of values that's reasonable, that lets you see that there's possibility that sample proportions will vary. Would you be pretty comfortable concluding that you have a majority? Would we be able to say the statistics show that we have evidence of a majority? And it's not because 60% is above 50. It's because the interval around 60% is completely above 50. If the interval had come down below 50% at all, I would not have statistical support for a majority, even if the sample rate was above 50%. We have to allow for that variability. All right, so we're going to build on this idea and talk about confidence intervals for the rest of today. That's chapter 10. As you're maybe doing some homework or practicing questions, you take out your formula card. And we have covered almost everything on the front page. The bottom right corner is about means, and we're doing proportions first. So that little part down there we're not going to use on the first exam. But we have already turned to the second page of the formula card, and this little top left square is where we're going to be using those formulas over the next about week or so. And that is where you find the standard error and where you'll see our first confidence interval that we'll be deriving here. So we've moved to page 2 of our formula card a little bit. Chapter 10 is about estimating proportions with confidence, deriving what are more formally now called the confidence intervals and understanding their interpretation. The first section is more of a review, sections 1 and 2, of just the idea that you've got a population and you take out of that population a random sample. You calculate something on your sample and you've got this statistic that helps to estimate the corresponding parameter. The fact that an estimate from our sample, a statistic will vary, and therefore you can talk about its standard error that estimates how it varies from that true value. You're going to see a number of confidence intervals before the end of the class this term. And each of the confidence intervals are going to have the same basic structure. It's always going to be your best guess. That's always the midpoint of your interval. And then you go plus and minus a few standard errors of that best guess. The few will depend on how confident you want to be, and the most common confidence level will be 95%. But we will be able to do 90 or 99% or whatever level you want. And that confidence level will be important to understand how you truly interpret it. So let's take a look at how we'll build our first confidence interval for a proportion P. It really comes from this model that we highlighted at the beginning that describes how that sample proportion P hat tends to vary. So the first picture you've got there is to draw this normal model. I'm drawing the model for P hat. The model that describes the distribution of that sample proportion. The values that P hat could take on if you sampled over and over. Thus a sampling distribution. And the true proportion, P, is where this normal distribution is centered at. And the standard deviation, again, for a proportion had the n on the bottom, P1 minus P over n. I'm going to just call that the standard deviation. And what we're going to do is follow through steps 1 through 5 and use our picture to animate some of these ideas. So there's our model for how values of a sample proportion will vary, normally around the truth, and there is some give or take. The first step says, first draw an interval or range of values that goes plus or minus 2 standard deviations each way. So here's my tick marks, 1, 2, 1, 2. So I'm going to go plus or minus 2 standard deviations each way. This upper one will be then P plus 2 standard deviations, and the true proportion P minus 2 standard deviations. So if I could calculate those and have those values, what do you know about the probability of seeing something in that range? If I were to go out 2 standard deviations under a normal curve, it only works for bell curves, remember, but a normal curve, then I would have about 95%. So question 2 says, what's the probability that you will see a sample proportion in that range? There's a 95% probability that if I were to take a sample of that given size n, that I'll get a sample proportion that close to the truth. All right. So now what we're going to do is pretend to take samples over and over and calculate that value of P hat. So let's suppose that our first sample, random sample number 1, turned out to give us a sample proportion that was a little bit underestimating. Suppose that sample proportion ended up falling right about here. So here's our first P hat. Not quite 1 standard deviation below the truth. And if I start with that value and I go out 1, 2 standard deviations each way, so the same distance each way as I had initially, and that forms my first confidence interval, did this first interval around the first sample proportion that we ended up getting contain the true value of P? Is the true value of P in that interval? Yeah. It is here. It was a good interval. A good interval would be an interval that does actually have the true value of p in it, because that's what I'm hoping my confidence intervals will provide for me. An interval that is good. What would happen if I did it again? What if I take another random sample? Same size from the same population, I will likely get a different population or sample proportion p hat. Let's suppose that that one is a little bit high this time, more than 1 standard deviation above the mean. But I still go out 1, 2 standard deviations each way and get my next confidence interval. How about that interval? Would you call that a good one too? Yeah. It's a different interval, different endpoints, but it is one that has the true proportion in it again. This is also a good interval. It has a true proportion p falling in it. Every time I get a sample proportion p hat that falls in that original range, 2 standard deviations from the truth, what will happen if I make the interval around that p hat? It's going to have the value of p in it. So how often am I going to get a good interval? How many samples, if I did it over and over, will give me a good interval? 95%. 95% of the results will give me an estimate that if I go 2 standard deviations from it, it would have the truth in there somewhere. 95% of the intervals are going to end up being good. What will happen occasionally, like 5% of the time? I'll get a random sample. The ith random sample somewhere is going to be a sample whose estimate is not as good. And even if I go 2 standard deviations each way, that particular interval will not have the true proportion in it. It's a bad interval. But this kind of interval will happen only what percent of the time? Only 5% of the time. That's why I'm going to be confident in the result I do get from my sample, because beforehand I had a 95% chance of getting a good interval. But each individual interval is either good or not good. If I asked you, what's the probability that that first interval contains the true proportion p, what would you say? What's the probability that first interval has the true proportion p in it? 100%. It does. That first interval has p in it, right? There's no randomness really anymore. If I already picked my sample and here's my interval, does it have p in it, that first one? Yep. What's the probability that the second interval has the true proportion p in it? 100%. It does. What's the probability this interval has the true proportion p in it? 0. It doesn't. After you've looked at the interval, there's no more probability. It either has the true proportion in there or not. You won't know whether the probability is 1 or 0 because you don't know the true proportion p in most problems. But in fact, every single interval that's actually produced either does or doesn't. There really is no more probability. It's just that I can't tell whether it's one of those good ones or not. All right, we'll keep that in mind when we have a couple questions later. The big idea on the next page highlights that 95% idea. Every time you take a sample proportion that's in the original 2 standard deviation away from the truth and go out 2 standard deviations from it, that interval will have the true proportion in it. 95% of the intervals made when you start at p hat that you get and go out 2 standard deviations are going to have the true proportion in them. That's what we mean by being 95% confident. Now, this could then be my first formula for a confidence interval, but I run into that same problem that we highlighted earlier. Try calculating that particular confidence interval when all you have is your sample proportion p hat. And you can't calculate that true standard deviation, but we have a fix for that now. We can't calculate the true standard deviation, but we can calculate the same kind of quantity, but just put in the p hats. And what was that called again? Not the standard deviation, but the standard error. We can use the standard error of our estimate instead. So our first boxed off confidence interval, our approximate 95% confidence interval for the true proportion, would start out with your best guess and go out to standard errors. That's exactly what we just did with that love at first sight example. It's approximate because we kind of learned that 2 standard deviations doesn't give you exactly 95%. When we worked with our normal table last week, we found it was a little more than 95%, but it's a good enough rule of thumb to still use. So let's do some calculations. Let's try it out with an actual set of poll results. And maybe as a quick highlight, look at this margin of error expression for me. And what happens to this whole expression if you put in for p hat 1/2? Think through that little bit of algebra. Put in 1/2 for p hat in both places. So you'll have a 1/2 here, and this will be again another 1/2. 1/2 times 1/2, it's under the square root, so you can bring it out. And what will happen with the 2 then? It'll cancel out. So you'll be left with 1 over the square root of n. When we put in 1/2 for p hat, we'll get our margin of error that we already know about, that 1 over square root of n. And that's an approach that's called being conservative. And we'll see that in a few moments. But for now, this is the general confidence interval with 95% confidence. And let's try it out with those teenagers that say they get along very well with their parents. So here's some survey results. The Gallup poll, organization that does a lot of surveys, a lot of studies. Just go to their website and you can see a lot of results. They have a nice description about their sampling techniques that explain that margin of error and that 95% confidence level idea. Survey of a little over 500 American teenagers, asking about how long they get how well they get along with their parents, and 54% of them said very well. So our sample size is 501. 54% is our sample proportion. P hat is 0.54 here. Do we know the true value of P? No, that's why we took the survey to estimate that true proportion. And the 0.54 is our best guess right now. But often it's better to give that best guess along with that standard error, so you can get an idea of how far away that guess could be from the truth. So let's calculate that standard error one more time. Standard error of p hat. Again, the second page of your formula sheet would be providing that actual formula. We'll be plugging in here the 54% now. And we have a sample size of 501. Under the square root, you get a really small number, 3 zeros, and then a 4958. I carried out a bit in this step because at the very end I can do that little bit of rounding. And I do get, with rounding, still about 2.2% here. 54% is my best guess. 2.2% represents that approximate average distance. Can we fill in the blank for another good interpretation of a standard error? Yeah. Do it. Last step again. That's the square root of this small number. So when you get the variance estimate underneath, it could be a really small number with scientific notation maybe in your calculator. Take still the raised to a 1/2 or the square root, and you'll bring it back to about 0.22. All right, so we would estimate the average distance between the possible values and what? To be about 0.22. We would estimate the average distance between the possible, what kind of values are we talking about here that vary? What is it the standard error of? The sample proportion, p hat. We would estimate the average distance between the possible sample proportion values, or p hat values, and what? We're always looking at the distance of those values from their mean, but what is the true mean of the p hat values? When you draw a model for p hat, it's centered at p, the true proportion, the population proportion. So we would estimate the average distance between these sample proportion values and the population proportion p to be about 0.22. I calculate the standard error and I now have an idea of how far away those sample rates, sample proportions would tend to be from the true proportion on average. All right. The key here is we have an estimate of that average distance because we don't have the actual standard deviation. Let's use that standard error and let's make our confidence interval. A 95% confidence interval for that population proportion. Notice that we say it's a confidence interval for p. It's not a confidence interval for p hat. I'm using this interval as an estimate for what I think might be p. Confidence interval for p. So what do we want to do? P hat plus or minus a few standard errors. The few will be 2 here since we're 95% confident. Again, I have some students, those that have not come to class, putting in 2. They'll put in the standard error, and then they'll still put in 0.54 and multiply that at the end, because they don't know that's the standard error of p hat. Margin of error, about 4.4%, and this interval does go slightly below the 50% mark. So on your next homework 3, you'll have to calculate at least one confidence interval. And the calculating of the interval usually isn't too bad, even on an exam. You put in your estimate, which I have to give you in some form. You might have to work out that standard error. But you can come up with those two numbers that form the interval. And then after that, it will typically be a couple questions. One would be to write a sentence so that you can describe for me what that interval means. I mean, what do those two numbers tell you? So that's back in the context of the problem, talking about proportion of teenagers that get along very well with their parents. And then there will also be the issue of explaining to me what you mean by being 95% confident about your interval. So in part C, we just fill in the blanks here, and we've got a nice interpretation of the interval itself. So this is interpreting the interval. Tell me those two numbers in the sentence and put in the context of the problem. Based on our sample, even putting in there how confident I am, 95% confidence, I would estimate somewhere between what? 49.6% and 58.4%. Somewhere between those two rates to be the rate for all American teenagers that think they get along very well with their parents. Just putting those two numbers into a sentence so I know what they mean in the context of the problem. I now would estimate somewhere between 49.6 and 58.4% of all teenagers get along very well with their parents. It's my interval estimate for that true proportion. D and E are two statements to help us see if we can understand what that confidence level means. So I want to give you about 30 seconds to read through D and E, and we're going to click in whether you think that is a correct statement or not for two of our clicker questions here in the middle. So read over D and E, and I'll ask you for your opinions here in a moment. So part D says, can we say the probability that our interval that we just got contains the population proportion is 0.95. And my hint would be to think about the picture that we drew a page or two back with the normal curve and some of the comments we made there on page 74. And tell me if you would say this is a correct statement or incorrect. Does your neighbor agree with you or not? Some of you are convincing your neighbor to go in the right direction. Still could be better. All right, I'm going to call it 5, 4, 3, 2, 1. And the latest trend was going in the right direction. That's good to see. Here are the results. And as soon as it tabulates all the votes, I will show you that the answer is no. Why? Originally it was 80-20. Some of you were convincing in the right direction. And I ask us now because these are the kind of results I see the first time when you approach this. Do you remember the picture we drew? And every single interval either had the true proportion in it or it didn't. I even asked you, what's the probability that one first interval right there that you already calculated has the true proportion in it? And you said at first 95%, but then we said it was going to be 100%, 1. When you've already calculated the interval, those two numbers are now fixed. And the value of p, that true proportion, is a fixed number. It's not a random quantity. There is nothing random about that event that's in the parentheses. The true value of p is either between those two numbers or it's not. It's like pulling the ball out of the basket and you know that half the ball, or say 95% of the balls are blue. And you pull the ball out of the basket and I ask you, okay, here's the ball. Is it blue or white? And you'll be able to tell me the answer if you are not colorblind. The idea is we're kind of colorblind. We don't know whether the ball is blue or white, but it either is or isn't. When you pull your interval out, that either has a true proportion in it or it doesn't. I just can't tell you whether it is the 0 or the 1 because I don't know the true value of p. If I knew the true value of p, I could tell you it's in there or not. The probability applies before you look, before you pull the ball out of the basket, before you take your sample, you will have a 95% chance of getting a good interval. But once you've pulled the sample out, that either is a good result or not. This probability is either 0 or 1. P is not random. P is not a random variable. P hat is, but not P. We just don't know whether the probability is 0, it's not in there, or it's 1. I'm still hoping that my interval is a good one. But when I put it out there, make a decision based on it, it was either a good interval or not. Before you look, you know there was a 95% chance, but after you look, no more random pieces there. All right, what about part E? Can we say 95% of the time the population proportion will be in the interval that we computed already, in this interval? It's a slightly different way of phrasing things. "95% of the time, the true proportion will be in that interval, from 496 to 584. Better. All right, answers in, and here are the results. It is again a no. "95% of the time, that true proportion will be in that one interval you already calculated." Does P hop in that interval 95% of the time and stay out of it 95% of the time? Does that value of P change? No. P is fixed. It's some fixed, unknown, true proportion. I'm trying to learn what it is. I took my one sample out, got my one interval. It was made with a good method, but that one interval either has the true proportion in it or not. That true proportion doesn't jump into that interval 95% of the time. It's either in that interval or it isn't. The key is, again, in that interval we already computed. Because once you made the interval, it's either a good one or not. Once you've made a decision using statistics, it's either right or wrong. But the methods we use that we're going through together are good methods. Those methods work 95% of the time. 95% of the intervals will have the true proportion in them. I just don't know whether this interval does or not. If I'm running a polling agency and I use statistics behind each of my polls with sound random sampling, 95% of the results I'm putting out there are good results if I do them with 95% confidence each time, and only 5% are not. I can't tell you which polls were bad ones, but 95% are good. So let's work this out. Top of the next page gives you a bit from the text on what they have for interpreting the confidence level. The key part, they say it is a probability, but they talk about it in terms of the method. It's about that yet to be constructed interval. You can only talk about it before you look. If you did calculate all the possible samples, and thus all the possible intervals, that confidence level is this fraction or percent of those intervals that will include the true proportion. So what we're going to do is write up a really good interpretation at the bottom of this page that you can go back to and rely on for writing up an interpretation in the future. I'd like to start out with that phrase that our interval was found with a method which, if repeated over and over. So talk about the method. And if you were to do the method over and over, what could you say about those results? In other words, my interpretation of the confidence level is not even going to include the 496 and that 584 number. It won't even include the interval I got this one time. My interval that I got was found with this method, which if repeated over and over, what would happen? If I keep doing it over and over, do you just have one interval, the same one every time? You got lots of intervals. If I repeat it over and over, would generate, would provide or give me many possible confidence intervals. What would we expect if we looked at that collection of those many intervals? We would expect what? What percent of those intervals will be good intervals? 95%. We would expect 95%, not of the time, but 95% of the intervals. I'm saying here to be good, but what would that mean in this context? To have the true proportion in them. 95% of the intervals we'd expect to contain, and here's what we would write out for this context, the population proportion of all teenagers who get along very well with their parents. That takes a long time to write that whole thing out. That's why we like a little notation here and there. What is that population proportion of all teenagers who get along very well with their parents? In shorthand symbol, that would be P. So if you identify P up front, you can just write P there instead. We would expect 95% of the intervals to have the true proportion P in them. Say it that way rather than 95% of the time, or try to use anything about your interval you just made. That's interpreting the confidence level. In part C, on the previous page, that was interpreting the interval itself. You have to use the numbers in that interpretation, but the confidence level is a property about the procedure you used, the method that you used. You will see a great applet that you get to play around with, a simulation, for your pre-lab 3. It'll be available by tomorrow sometime if you want to look at it at that point. You just play around with a couple of the numbers. You change 95% to 99%, and you see what happens. Click of a button produces a whole bunch of intervals for you. So you can see what percent end up having that true value in them. And look at a few results. All right. The next question I'm going to let you try on your own. I will post it up on C-Tools, the top of that page 78. We have 2 last ideas and confidence intervals we want to go through. But to take our little break, I don't have a picture of the day. I have some hidden meanings. So last week was the end of a semester for my daughter, and one of her homeworks after the exam was taken in the class was this list of hidden meanings. You had to come up with the phrase or what it was saying. So here's the first one. I heard it already. What word is it? It's decision, and it's a split decision. Yeah. And here's another. This was harder. That word time is very long. Long time, no see. Long time, no see. I'll share with you a few more in another class or two. They made me think. All right, now let's go back to thinking about statistics. If we want to be 95% confident, we go out 2 standard errors. 99.7% confident, we'll go out 3 standard errors. How do we change our confidence level? What will be the right multiplier for it? So we first want to figure out, again, reminding us that 2 does work for 95%, and see then how we would change things if we want to be a different level of confidence. So the exact multiplier for 2, or for 95%, is actually not 2. It would be 1.96. And let's use our normal table to figure that out. So I want to find this value plus and minus that I would go out so that I have a certain level of confidence in the middle. And our first level of confidence was 95%. So if there's 95% in the middle, then how much is left over in the 2 tails together? 5%. How much is left over in each tail then separately? 2.5%. So there's 0.025 here and 0.025 here. So if I'm asking you to find this value of z on this axis so that there is 95% here and another 2.5%, 97.5% to the left, then we can look that up from our formula card, our table A1. Your table A1 is back in the 50s, I think, maybe 56 or so. How do we look up a percentile for a normal distribution? Got to do it on your last homework question. That's due tomorrow night. That very last question, part B, was looking up a percentile. I want to look up 97.5, 0.975 in the middle of your table. What page is that on from before? 50? It is 56. You want to look it up. 0.975 in the middle of the chart? Oh, that's exactly right there. What is it? 1.96. 1.96 would give you the exact 95% in the middle. Closest value of z is 1.96. 1.96 and a negative 1.96. So that's how you actually find the cuts, these multipliers. They're called z stars because they're just these particular percentiles from your normal table that give you that desired confidence level in the middle. So for 95%, we use 2, and if you use 2 on an exam for 95%, I'll accept that. But the actual number to get exactly 95% is 1.96. A couple other common levels, maybe 98%, 99, 90. So I want you to try to find one more for me for the 90% level of confidence. Use the picture in the same way and look it up from your table A1. What's the multiplier for 90% confidence level? So try finding that value. So if I want 90% in the middle, I actually have to look up the 95th percentile. Because your table's set up with areas to the left only. So you can't go to the table in the middle with 90% because that's not what the table gives you. It gives you the total area to the left. Go to the table with 0.9500, and you fall exactly in between two numbers, right? What would you get, 1.64 or 1.65? I'd accept either one of those. Isn't that similar to the one in your homework? I think. It actually is 1.645. Ends up being exactly in between. I'd accept either one because it's equally as close. The actual value is 1.645, and if you brought your set of tables, you can peek ahead to this table A2. It's also shown on the next page or highlighted. Table A2 is an easier way to find those same z-star values. It's at the very bottom of the table. Go under the confidence level column and you'll find exactly those z-stars. You also have a table that comes from the text which gives you those common multipliers for common levels of confidence. Table A2 will be used when we do means and T procedures, but the very bottom row has the multipliers for z-star. They're under the infinite row, and there's 1.645, there's 1.96. So you can use that little table A2 to find those values directly. without having to draw the picture. Couple comments. What happens if you want to be more confident then? Your multiplier goes up or down? Up, gets larger. So if you want to be more confident, your interval has to be wider. Does that make sense? I want the method to be more accurate. I want the probability that I will be getting an interval that has a true value in there to be higher. So that interval is going to have to be wider to have a better chance of having the true value in it. Higher level of confidence means your interval is wider. That means a larger margin of error. You're not as precise, but you can be more confident. All right. There's a couple more comments on that page that show you the box in the middle. These are great boxes. What I like about them the most is that they clearly give you the conditions that are needed to do that inference technique. Here's your general confidence interval now. It doesn't have a 2 sitting there. It's got a Z star, because you can be whatever level of confidence you want to be. It tells you that standard error and how to find it. It gives you the 2 conditions. We're always going to require that our samples are representative. So the sample needs to be a random sample, randomly selected from the population. Remember that fundamental rule that we had back in chapters 3 and 4. And then the only other condition I need that allows me to use the normal curve to look up that Z star is that you took a large enough sample size. If I didn't take a large enough sample size, I'd have to go back and do some kind of binomial confidence interval, which is a little complicated actually. We're going to always require a large sample size so we can make this interval. And here again are the conditions. Now here's where I run into trouble. I can't check those conditions as they are listed there. I don't know p. How can I check if n times p is at least 10 if I don't have the true value p in this kind of a problem? So then you have to put in your p hat. And make sure in your sample you got at least 10 yeses and at least 10 nos. That's the best you can do to check this condition. So our last condition there says you need that at least 10 rule to hold, and we of course will check this last one by using n times p hat being at least 10 and the n times 1 minus p hat. And I've had some students in the past mention whenever you talk about 1 minus p, which is your failure rate, that's like Q in some other books that have been used. And P and Q represent the rate of success and failure, but we have the 1 minus P. So you have to check it with that value instead. The confidence interval at the bottom is just calculated for you using a 90% level instead. Notice that the interval here for the proportion of teens that get along very well with their parents is a little narrower, as you would expect. Bottom of page 79. The 90% confidence interval will be narrower because the multiplier is smaller. With 90% confidence, would you have been able to conclude a majority? Is this interval completely above 50%? Yeah, so you would at a 90% level of confidence, but you could not reach that conclusion at a 95% level of confidence. Do you see why the confidence level needs to be established up front? Tell me how confident you want to be up front and then go through the procedure, not pick it afterwards so that you can say you have a majority versus you don't. Also notice that it's still centered at 54%. One of your, was it a homework question? It was an exam question. I give you the interval. If you have the interval, you've got 2 things. If I give you the interval, and I'm going to make the numbers a little easier, and it goes from 60% to 80%, and that was my confidence interval for the true proportion, what must have been my sample proportion, p hat? Where does the sample proportion sit in every interval? Right in the middle. So the sample rate must have been 70%. 70% of my sample must have said yes. And what's the margin of error that goes with that 70%? Went down to 60% and up to 80, so the margin of error is 60, 70, 80. 70 to 80, 10%. 70 to 60, 10%. The margin of error would be 10%. Every interval provides you with the two things, your best guess, which is always the midpoint, because that's how the interval's made, p hat, plus or minus, and there's that part that comes after that's called the margin of error, and that margin of error is the half width of your interval. It was based on your sample size and your confidence level that you decided to use, but you always have that from the interval itself. It was 10% here. You could actually almost work out then what the sample size must have been, kind of backwards. All right, we aren't going to take the time to work through the conservative side. We'll do that together on Thursday and start into hypothesis testing. Have a good day.